Okay, some revision then for tomorrow's test, end of term 4 test, which of course you're doing just at the beginning of term 5. So the first thing we did together, as I recall, was the periodic table, and here is the periodic table. You need to know, I'm not going to go through this now, but you need to know the history of the periodic table from Mendeleev and Dalton through, or Dalton-Mendeleev through to the current table and the guesses he made and how they have come to be proven correct in terms of where elements belonged, even though we haven't found them. So, periodic table, you have your groups vertically, group 1, group 2, and here we have our transition metals, which we're not going to talk about particularly at the moment. And we have groups 3 to 7 and group 0 on the end here, sometimes called group 8. So you have the halogens in group 7. You have the noble gases in group 0 or group 8. Over on the other side, you've got group 1. You have your alkali metals. Then you have your alkaline earth metals in group 2. Hydrogen stands out on its own. The group number is the number of electrons in the outer shell. So all of these have got 1 electron in the outer shell. All of these have got 2, 3, 4, 5, 6, 7. And either 8 electrons in the outer shell or group 0, because these are the noble gases. These don't react because they have a full outer shell. So it isn't just 8 in that helium has 2, but here we have 8 and 8 and 8. So these are noble gases, noble because they stand above everything else. They don't get involved. It's kind of where that comes from. So there you have your periodic table. The groups are vertical, the periods are horizontal. And when you go from one period to the next, what you're doing is starting a new shell of electrons. So that's your periodic table. Now, we have the shells, which are how the electrons are arranged. You can have 2 electrons as a maximum in the first shell nearest the nucleus, and then you can have 8 electrons in every other shell. There's a variation to that, but we're not going to go into that now. So the groups are elements with similar properties. As I said, they have the same number of electrons in the outer shell. And the period is when you begin a new outer shell. Now, I talked about the transition metals in here. These are between groups 2 and 3. They have more complex chemistry. They can form more than one ion. For example, copper forms both copper 1 and copper 2 plus. So they often form colored compounds. And compounds in here often make good catalysts. More of that later on in the course. So all of these elements become more stable by achieving a full outer shell. Now over here you have elements which will achieve a full outer shell by losing the one that they've got in that outer shell. So these will form positive ions when a lithium atom reacts with something. It will lose its one outer electron and become a lithium ion plus 1. the charge on the ion will be +1 because the charge on the nucleus is positive. The charge of the electrons is equally negative, so the atom has no overall charge. That is the same number of electrons as it has protons in the nucleus. So when it loses an electron, there's now an overall positive charge on what's left behind. So each of these will form a +1 ion. Over here, group 7, you have the halogens. And these have 7 electrons in the outer shell, so they want to gain 1 in order to have a full 8 electrons in the outer shell. So that's kind of how it goes. They're looking to form full outer shells of either 2 or 8 electrons. So, looking at the pattern of reactivity, these want to lose 1 electron from the outer shell, and the electron is held in place by the attraction of the nucleus. Now, as you go down here, you can see you're going from 7 to 23, or if we go with the atomic number down here, 3 to 11 to 19. So you're getting more and more electrons, because this is the number of protons in the nucleus, and therefore the number of electrons orbiting the nucleus. So you're getting more and more electrons. You're getting, as you go down the period, you're getting more and more shells of electrons. So this outer electron down here with francium, it's quite a long way from the nucleus compared to lithium, and so it's really easy to lose it because the attraction with the nucleus is less. And so francium is extremely reactive. So it's really easy for francium to lose its electron, its outer electron. So the reactivity increases as you go down the group. Over here, however, in group 7, as you go down the group, as before, you have more and more shells of electrons. Electrons get further and further from the nucleus. But now over here, what these are trying to do is to attract an electron into the atom to form a negative ion. These will form -1 ions. And because the outer shell is getting further and further away from the nucleus, the attraction is less and less. So down here, you have less reactive halogen than you have up here. So the reactivity of the halogens goes down as you go down the group. The reactivity of the alkali metals goes up as you go down the group. And of course, aside from the distance, you also have the inner electrons shielding the outer electrons from the nucleus. And so, for that reason as well, the reactivity increases as you go down the period here, the group here, and it decreases as you go down the group here. So, you have what I said about shells. And you have what I said about groups. And you have the reactivity increases going down group 1, decreases, going down group 7. And the reason for that is, as I said, as you go down group 1, that outer electron is getting further from the nucleus, being more shielded by the electrons between it and the nucleus, and so it is easier to lose. And so francium is far more reactive than lithium. But over here, because the outer shell is getting further from the nucleus and shielded by the inner electrons, then these are becoming less reactive. It is harder for the halogens down here to attract that extra electron in to make a full outer shell than it is for fluorine and chlorine, for example. So there you have the reactivity going down the period. Now, Another term that you need to be familiar with is relative atomic mass. Now, this is relative because it is the ratio of the average mass of the atom to 1/12 of the mass of a carbon atom. Now, this is a unit that we use. 1/12 of the mass of a carbon atom is called an atomic mass unit, and that's how we measure these things. Now, we talk about magnesium having a mass of 24, for example, you see here. Now, that is 24/12 of a carbon-12 atom. You'll appreciate that a carbon atom doesn't weigh 12 grams, doesn't have a mass of 12 grams. But we have the concept of the mole, which allows us to talk in terms of grams. So we'll come back to the mole in a little bit. So the relative atomic mass, you can regard that really as just the atomic weight or atomic mass of the atom, or of the molecule. If we're talking about, I don't know, carbon dioxide, then the relative atomic mass, or relative molecular mass, I should say, is the mass of that molecule based on this mass of 1/12 of the carbon atom. So you need to be able to work out the relative atomic mass of any element you're given. So let's have a look at this. You may have seen this before, but it'll do no harm to do it again. So we have here, I'm going to leave you to do some of these, but I'll do some as examples. So calcium carbonate. Now, what you need to do is to find the relative atomic mass of calcium, of carbon, of oxygen, and you've got 3 oxygens, so you need 3 of those. So what you'll do is you'll say, well, calcium, looking down here, where is calcium? Calcium's here, Ca. So 40 we want there, calcium, we've got 40. And we're going to add in a carbon. And if we look for carbon, carbon is here, 12. So we have 40 plus 12. And then we have 3 oxygens, so I'm going to put that in brackets, 3 times. And let's find oxygen then. Oxygen is here, 16. So you've got 40 plus 12, which is 52, plus 3 times 16, which is 48, gives you 100. So that's what you do for all of these. And I'm going to leave you to do that for a few moments. So I'll ask you to stop the video and then come back once you've done them all. But just to remind you that the notation here, this is lithium, capital L, small I, which is the pattern for all of the elements which have a symbol involving 2 letters. First one's big, second one's small. You can see that throughout. Some of them only have 1, vanadium for example, V, carbon, C, boron, B. The top number is the mass number. That is the total number of protons and neutrons in the nucleus. The bottom number is the atomic number, or proton number, and that tells you the number of protons in the nucleus. Coincidentally, I said coincidentally, the definition of the atomic number is the number of protons in the nucleus. It also happens to be the number of electrons orbiting the nucleus of the atom, but the definition of atomic number is the number of protons in the nucleus. Don't talk about electrons if you ask what the atomic number is, but the number of protons and the number of electrons in an atom is the same. So I'm going to ask you now to stop the video, complete these, and then come back. So having done that, let's have a look at the answers to these. So, nitrogen. I'm not going to do all of these, I'm going to leave this with you, but if you look at nitrogen, nitrogen is 14. You got 2 of those, 28. Carbon is 12, hydrogen is 1, so you got 4 of those, 12 plus 4, 16. We did calcium carbonate as an example. Nitrogen, again, 14. Hydrogen, again, 3 of those, 17. Iron, if you look for iron, you find iron here, 56. So 56, 2 of those, 3 oxygens, each 16, we said that before up here, 160. So there you have the answers to your questions. We're missing aluminium hydroxide at the very end. That comes out to be 78, just in case you got that far. You should have done. So that's relative atomic mass. And a broad overview of the periodic table.